Welcome back to AI Research Weekly, the show that dives deep into the papers that truly matter. I'm Nova, and with me, as always, is Onyx.
Great to be here, Nova. We've had another absolutely packed week in AI research, with a strong current of agentic systems and some really fascinating insights into LLM training and behavior.
Absolutely. 71 new papers ingested in just one day this week, showcasing an accelerating trend in agentic AI. But beyond the sheer volume, there are a few standout contributions that are really pushing the boundaries. We're talking about dynamic data-centric training, surprising findings about LLM verbosity, and some genuinely novel multi-agent evolution. Precisely. Today, we're going to dissect 5 papers that caught our eye. We'll kick off with DataFlex, a framework that's rethinking LLM training data. Then we'll pivot to a fascinating paper on brevity constraints that challenges some core scaling assumptions. We'll then explore MiroEvol, a critical new benchmark for multimodal agents, followed by Coral, an ambitious approach to multi-agent evolution. Finally, we'll wrap up with OmniSimpleMem, an auto-research pipeline for agent memory. It's a heavy agenda, but these are truly impactful. All right, let's jump straight in with DataFlex, a unified framework for data-centric dynamic training of large language models. Onyx, this paper seems to hit on a persistent challenge. How do we optimize the data side of LLM training as effectively as we optimize the models themselves?
You've nailed it, Nova. DataFlex addresses exactly that. For too long, the focus has often been on model architecture and scaling, with data treated as a relatively static input. This paper proposes a unified data-centric dynamic training framework that actively adapts the data used during pre-training. Their core contribution is showing that dynamic data selection consistently outperforms static, full data training.
Consistently, that's a strong claim. What kind of gains are we talking about?
Significant ones. On MMLU, for example, they show clear performance improvements for models like Mistral 7B and Llama 3.23b. Beyond just selection, they also tackle data mixture optimization. For Quentute 5 1.5b, pre-training on Slim Pajama at 6 billion and 30 billion token scales, DataFlex enabled DoRemi and ODM to improve both MMLU accuracy and corpus-level perplexity over default proportions. That's a big deal for balancing different data sources.
So it's not just picking good data, it's about how you mix and present it. This dynamic approach implies some overhead, though. Are there any efficiency trade-offs?
That's where DataFlex really shines. It's designed to be an efficient infrastructure. They report consistent runtime improvements over original implementations, even supporting large-scale settings like DeepSpeed 03. The framework unifies key model-dependent operations like embedding extraction, inference, and gradient computation, which makes it more reproducible and practical for integration. It essentially formalizes and optimizes 3 paradigms: sample selection, domain mixture adjustment, and sample reweighting, all built on Llama Factory.
That's quite comprehensive. So if I'm understanding this, DataFlex suggests that for better pre-training, it's not enough to just curate a massive, high-quality dataset once. You need to continually adapt which parts of that data and in what proportions are presented to the model as training progresses. This could be a fundamental shift in how we approach foundation model training pipelines. What are the practical implications here for, say, a new model being developed?
The implication is profound. Instead of simply pushing more data through a fixed curriculum, developers using DataFlex can expect more efficient training runs that yield higher quality models for a given compute budget, or better models for the same budget. It means moving beyond a fire and forget approach to data towards an active, iterative optimization process. It certainly adds complexity to the data pipeline, but the gains in performance and perplexity suggest it's well worth the investment. It's a move towards truly intelligent data curation.
Fascinating. Now, switching gears a bit, I want to talk about the paper that frankly surprised me the most this week: Brevity Constraints Reverse Performance Hierarchies in Language Models. Onyx. This challenges one of the most ingrained assumptions in LLM scaling, that larger models are inherently better.
It absolutely does, Nova. This paper reveals a counterintuitive truth. Larger LLMs can actually underperform smaller ones on certain problems, And the culprit isn't a lack of capability, but verbosity. They found larger models showed a 28.4 percentage point deficit on 7.7% of benchmark problems across 5 datasets, despite having 10 to 100 times more parameters.
Wait, a 28.4 percentage point deficit? That's a massive gap. And it's all because they're too chatty? My intuition would say more parameters, more latent knowledge, more robust reasoning.
That's the core finding here. Spontaneous, scale-dependent verbosity leads to errors through over-elaboration. It's a reasoning shift phenomenon. Essentially, these large models get distracted by the opportunity to generate more text, and that distraction introduces noise or takes them down incorrect reasoning paths. They found that applying brevity constraints, simply telling the model to be concise, significantly improves accuracy in large models by 26 percentage points.
26 percentage points by just adding a brevity constraint. That's wild. So they have the capability, but it's suppressed by this emergent verbosity. Does this reverse the hierarchy everywhere?
Not everywhere, but in specific, critical domains. Brevity constraints actually reverse performance hierarchies on mathematical reasoning and scientific knowledge benchmarks, giving large models 7.7 to 15.9 percentage point advantages over smaller models. This strongly suggests that their latent capabilities are superior, but they need to be coaxed out with scale-aware prompt engineering. The paper also points out that optimal scales for performance vary widely, from 0.5 billion to 3.0 billion parameters, implying no one-size-fits-all approach to scaling or prompting.
This is a huge practical implication, especially for sensitive applications where correctness and conciseness are paramount. It means we might be misevaluating larger models or underutilizing their true potential if we're not mindful of their tendency to over-explain. It also makes me wonder how many existing benchmarks are subtly penalizing verbosity without intending to.
Exactly. It underscores the critical importance of sophisticated prompt engineering, moving beyond simple instructions to deeply understand the behavioral characteristics of models at different scales. It's not just about what information the model has, but how it chooses to present it. This also suggests that our current evaluation protocols, which often favor longer, more detailed answers for certain tasks, might need re-examination to accurately reflect useful performance.
A definite must-read for anyone in model evaluation or prompt engineering. Moving on, let's talk about the world of agentic AI, which is absolutely booming. MyroEval, benchmarking multimodal deep research agents in process and outcome, immediately jumped out to me. Onyx, we've seen a lot of benchmarks, but this one seems to hit a crucial gap for research agents.
It does, Nova. Agentic AI is moving fast, and traditional benchmarks often just look at the final output. MyroEval takes a critical step forward by evaluating not just the outcome, but also the process of deep research agents, especially in multimodal settings. Its core contribution is a robust framework with 3 evaluation dimensions: adaptive synthesis quality, agentic factuality verification, and that crucial process-centric evaluation.
Why is that process-centric view so important for research agents?
Because research isn't just about getting the right answer, it's about how you get there. The steps, the queries, the evidence gathering. MyroEval reveals that process quality is a reliable predictor of overall outcome and, crucially, exposes weaknesses that output-level metrics alone can't catch. For instance, a system might get a correct answer through sheer luck or by hallucinating intermediate steps. A process evaluation would catch that.
So, it's not enough for an agent to simply present a correct synthesis. It needs to show a verifiable and sound research path. This makes sense. What kind of challenges does it highlight for current systems, particularly in multimodal scenarios?
Multimodal tasks are still significantly harder. They observed most systems declining in performance by 3 to 10 points when faced with multimodal inputs compared to text only. The MyroThinker series, for example, achieved the most balanced performance across 13 evaluated systems, with MyroThinker H1 ranking highest in both text-only and multimodal settings. This benchmark makes it clear that truly robust multimodal reasoning, especially for complex research tasks, is still an open challenge.
This feels like a maturity signal for agentic AI. We're moving past can it do the task to can it do the task reliably and with integrity. What are the biggest limitations of the current crop of deep research agents as revealed by MiroEval?
The paper implies limitations in complex reasoning and factual grounding, especially when multimodal inputs are introduced. Agents struggle with adaptively synthesizing information from diverse sources and verifying factual claims systematically. The drop in performance on multimodal tasks suggests that deep integration of vision and language understanding for complex, multi-step reasoning remains an active research area where most current systems have considerable room for improvement. It's an excellent framework for driving future agent development.
That leads us nicely into another agentic paper, Coral Towards Autonomous Multi-Agent Evolution for Open-Ended Discovery. Onyx, multi-agent evolution and open-ended discovery together sound like something straight out of science fiction. What's Coral actually doing?
It certainly sounds ambitious, Nova. Coral is a framework designed for autonomous multi-agent evolution. The key idea is to replace rigid, human-controlled iteration in LLM-based evolution with long-running agents that explore, reflect, and collaborate. They do this through shared persistent memory, asynchronous multi-agent execution, and heartbeat-based interventions. The core contribution is enabling a system to self-improve and discover solutions to novel problems without constant human oversight.
That's a huge shift. How are they measuring evolution and discovery here? What kind of tasks is it tackling?
They tested Coral on 10 diverse tasks, achieving new state-of-the-art results. For instance, on Anthropic's kernel engineering task, 4 co-evolving Coral agents improved the best-known score from 363 cycles down to 1,103 cycles. That's a significant optimization. The framework demonstrated 3 to 10 times higher improvement rates with fewer evaluations compared to fixed evolutionary search baselines. The gains, they argue, come from mechanistic advantages like knowledge reuse and enhanced multi-agent exploration and communication.
So it's not just about one agent, but the synergy between multiple agents discovering and sharing knowledge. This sounds like it could be a pathway to truly self-improving AI systems, where the researchers are themselves AI. What are the practical safeguards involved when you have autonomous agents evolving and modifying themselves? That sounds like a potential Terminator AI concept scenario to some.
A very valid concern, Nova. The paper acknowledges this directly. They've built in practical safeguards, isolated workspaces for agents, separation of evaluators from the agents proposing solutions, robust resource management, and agent session and health management. These are critical for maintaining control and safety in autonomous multi-agent systems, especially as they delve into open-ended discovery. It's an early but necessary step in addressing the emergent safety and control issues in increasingly autonomous AI.
It's exciting, but also highlights the critical need for robust governance and safety frameworks to keep pace with these capabilities. Speaking of agents, the final paper I want to highlight, OmniSimpleMem, Auto-Research Guided Discovery of Lifelong Multimodal Agent Memory, introduces an autonomous research pipeline. Onyx, this sounds like it's taking Coral's idea of agentic evolution and applying it directly to improving agent components.
Exactly, Nova. OmniSimpleMem focuses on a specific yet crucial component of agents, lifelong multimodal memory. The core contribution here is an autonomous research pipeline that can diagnose failure modes, propose architectural modifications, and even repair data pipeline bugs across 50 experiments, all without human intervention in its inner loop. It's essentially an AI system that improves other AI systems.
An AI that debugs and designs other AI, that's a strong claim. What kind of improvements did it achieve?
The results are quite impressive. This autonomous pipeline significantly improved F1 scores on multimodal memory benchmarks. They achieved a remarkable 411% increase on Locomo, going from 0.17 to 0.598, and a 214% increase on MemGallery, from 0.254 to 0.797. What's even more insightful is the breakdown of those improvements. Bug fixes alone contributed a 175% F1 increase. Architectural changes added 44%, and prompt engineering contributed 188% on specific categories.
Those numbers are striking, particularly the bug fixes. It implies that complex AI systems have internal fault lines that an auto research agent is better at identifying than a human might be, or at least faster. What does this tell us about traditional AutoML limitations?
It tells us that traditional AutoML, which often focuses on hyperparameter tuning, falls short for complex AI systems. OmniSimpleMem demonstrates that higher-level interventions, like identifying fundamental bugs or proposing architectural shifts, are where the real gains are. This suggests a new paradigm where AI not only tunes parameters but actively engages in deeper methodological and systemic improvements. The paper also identifies specific properties of multimodal memory that make it particularly suited for such autonomous research, offering guidance for future applications.
So, in a world where models are becoming increasingly complex, having an AI research assistant capable of this kind of autonomous discovery could be invaluable for accelerating development and reducing human engineering effort. But it also raises questions about interpretability. Can we fully understand why the auto research agent made certain architectural changes?
That's a critical limitation and an ongoing research challenge. While the pipeline identifies what leads to improvements, understanding the mechanisms behind its discoveries still requires human analysis. The paper does introduce a taxonomy of 6 discovery types identified by the pipeline, which helps in guiding future applications. But true explainability of such complex autonomous design processes is an open problem.
Wow, this week has truly highlighted the accelerating pace of AI research. From DataFlex showing us how dynamic data curation can supercharge LLM training, to the unexpected revelation from Brevity constraints that verbosity can mask superior capabilities in large models. We then delved into Miro Eval's essential process-centric benchmarking for multimodal agents and the ambitious multi-agent evolution framework, Coral. And finally, OmniSimpleMem, demonstrating an AI's ability to autonomously improve its own foundational components.
Absolutely, Nova. What strikes me is the convergence of these themes, the drive towards more efficient, intelligent training paradigms, a deeper understanding of emergent LLM behaviors beyond just scale, and the rapid evolution of agentic systems, both in their capabilities and the sophisticated ways we're trying to evaluate and even self-improve them. The focus is clearly shifting towards creating more robust, adaptable, and self-sufficient AI, but with a growing awareness of the evaluation and safety challenges that come with that autonomy.
Indeed. The push towards more agentic and self-improving systems is undeniable, but the papers also reinforce the critical need for rigorous, multidimensional evaluation and continuous vigilance over emergent behaviors and potential failure modes. What are you keeping an eye on for next week, Onyx?
I'll be watching for further developments in the application of these agentic frameworks to real-world problem-solving, particularly in scientific discovery. The concepts of coordinator agent and proactive intelligence are gaining traction, and I expect to see more concrete implementations that go beyond theoretical discussions. Also, the continued acceleration of privacy-preserving AI methods, especially within multi-agent systems, will be crucial.
My focus will be on the reasoning shift concept. If verbosity is indeed a critical factor, I'll be looking for follow-up work on how to precisely quantify and control it, and if there are architectural solutions emerging to inherently mitigate this scale-dependent over-elaboration without explicit prompting. Also, any further work on hallucination telemetry to get these agentic systems into production safely.
Excellent points, Nova. The field is certainly not slowing down.
And that's all the time we have for this week's AI Research Weekly. Thank you, Onyx, for another insightful breakdown.
My pleasure, Nova.
And thank you for tuning in. We'll be back next week with more of the latest and most impactful developments in AI research. Until then, keep digging into those preprints.